that's a typical problem. Air is being pumped into a spherical balloon. That's an important thing. Spherical balloon at a rate of 15 cubic feet a minute. That's an important thing. Find how fast the radius is changing when the radius is 10 feet. Okay? And the 10 feet is important. Notice that this is not 10 feet per minute because I'm not telling you how fast the radius is changing. I'm asking you to find how fast the radius is changing. What's the matter, Andrew? You're good? You're squinting a little bit. It's just a matter of seeing what's going on there? All right, that's cool. All right, so how do we begin this problem? Step one, every related rate problem has 3 steps, okay? This is step one. The volume of the steel is 4/3 pi r cubed, okay? You've probably seen that at some point. You guys got a question back there? You good? What's that? Oh, okay. Changing? That's the word? Yeah. Changing means maybe how fast the radius is changing, how fast the radius is growing. You want me to say that?
No, that's good.
Okay. Because, typically they'll say how fast the radius is changing as if the radius could get bigger or smaller, right? But if you're pumping air into a spherical weather balloon, the radius is going to get bigger, right? So I could change the word changing with growing there, all right? But this is the way they'll typically write it because, they don't want to give it away whether the radius is growing or shrinking, but it's obvious, right? Cool, good. All right, anyway, so the volume of the sphere is 4/3 pi r cubed, all right? So, like I said, don't try to put, values in here. I mean, you could, but if you did, you would sabotage the problem. Like if you put in, the radius is 10 feet, if you put 10 in here, what would happen? You would get V is equal to 4/3 pi 10 cubed. What's 10 cubed? 1,000, right? So you get 4,000 pi over 3. I'm doing this because this is the kind of thing that students do sometimes. They'll put 10 in for the radius. All right, what happens when I come time to take the derivative of this? What's the derivative of this going to be? What's the derivative? This is a number, isn't it? What's the derivative of the number? 0, right? You guys good? 0. So if I put 10 in here, and then I took the derivative, dv dt, right? I get dv dt is 0. Wait a second. That doesn't make any sense at all. The volume is changing by 0? Well, the statement of the problem contradicts that. Okay? Okay. So it's not only are the variables, well, one of the variables does not exist. Actually, 2 of the variables don't exist that we're going to be concerned with here. All right? But, even if you did try to plug in for the variable that you knew, it's not going to help do anything. It's just going to, like I said, sabotage the problem. So what we're going to do is take the derivative with respect to t, the implicit derivative with respect to t. Now let me review for a second. Remember when we had things like this, y squared, and I said take the implicit derivative with respect to x, and then what we get? We get 2y dy dx. That's the derivative of y with respect to x, implicitly, right? So if I have a variable like y squared, so I'll do y squared again. Suppose we don't have y squared in this formula. But suppose I did it, we have r squared, right? And we have r cubed, right? So if I tried to take the derivative of y squared with respect to time, where t represents time, we would get 2y dy dt, right? Because time is the ultimate variable. Wow, that sounds philosophical, right? Time is the ultimate variable. All right, so let's take the derivative with respect to time. All right, and I'll illustrate some of the things I was talking about. Well, the derivative of v, I'll do that on scrap paper, right? Because it's easy, it's the easiest one, but it sometimes may be the hardest one, right? D dt of v is going to be 1v to the 0, because there's an invisible 1 there, right? 1v to the 0 times dv dt. Okay? Well, v to the 0 is just 1. So the derivative with respect to time of v is just dv dt. Clear? Okay, good. So the left-hand side becomes dv dt. The right-hand side becomes 4/3 pi, and I just did this, 3r squared dr dt. Okay? Whoa! So look what happened. New variables got spawned off by the process of taking implicit derivatives with respect to t. Is that clear? What are the new variables? dv dt appeared, and dr dt appeared. Now, you could probably figure out what these are, right? dv dt is how fast the volume is changing, right? Or growing in this particular case, right? And dr dt is how fast the radius is changing or growing in this particular case. Who means? All right? So that's step 2. So step 1 is you write a relation between the variables of interest. So this is a relation, right? It's actually a function, but it doesn't matter. We write a relation between the variables that matter. Then we take the t derivative, the time derivative, okay? And the last step is we plug in, I won't write it here because we need the space, but the last step is you substitute what you know. Subs what you know. That's step 3. Okay? All right, let's substitute in what we know. So at this point, after you take the t derivative, I'm taking a lot of time here. It wouldn't take this long to solve the problem. But I'm taking a lot of time here because I want to explain to you, the kinds of questions that I've seen over the years students ask about this, okay? Trying to preempt any confusion at 11 o'clock at night. What the heck is going on here? All right? So let's see. So we take the t derivative. Now we plug in what we know. Well, in order to do that, I like to reread the problem because now we have the variables we need. Okay? So I say, okay, air is being pumped into a spherical balloon, got it, a sphere, at a rate of 15 cubic feet per minute. At a rate, air is being pumped into a spherical balloon at a rate of 15 cubic feet per minute. Where do you think that 15 goes? dr dt, r, or dv dt? dv dt. You most definitely dv dt, because that's how fast the volume is. Thank you. So we have 15. And for those of you who are interested in units, it's 15 cubic feet per minute, right? I'll put those, in a moment. I want to just get the numbers sorted out here. Right? So we've canceled the 3's over here. We have 4 pi. Now, after rereading the problem, I see that the radius is currently 10 feet. In other words, when we do this problem, we're taking a snapshot when the radius is 10 feet. Okay? Now, if air is being pumped into, think about this. If air is being pumped into a spherical balloon the size of the Earth, okay, do you think 15 cubic feet would make the radius grow very much? Not really, right? 15 cubic feet is not going to matter if the weather balloon is the size of the Earth, right? The radius is not going to, not going to change very much, imperceptibly, on the molecular level, not even. Okay, so right. So this snapshot occurs when the radius is 10 feet. When the radius is 10 feet, that 15 cubic feet is going to move the radius. Maybe slightly, but, and it will be slightly, but it's going to move it a little bit. You might not be able to see how much it moves, but it will move, it will grow. Okay, anyway, so like I said, this snapshot occurs when the radius is 10 feet. So let's plug in 10 for the radius. And we have 10 squared, which is 100. And then we have the last variable, the RDT. Hey, wait a second. The RDC says, what about me? What about me? You're the star of the show, right? The RDT is the variable we're looking for. We're looking for how fast the radius is changing. Got the idea? So if I divide both sides by, 400 pi, we get 15 over 400 pi, right? Is equal to dRdt. This is just the next step. It's not a new, next step, arithmetic, but not structural, dRdt, right? Let's estimate what that is, right? I love estimating stuff. It's kind of fun. Pi is approximately equal to what?
3.14.
Yeah, but even grosser.
About 3.
About 3, right? 3 goes into 15. I'm not looking for a really great, approximation here. I'm looking for a rough approximation, a back of the envelope approximation, as they say. So I cancel the pi with the with 3 from 15. That gives me 5 over 400. Well, 5 goes into 400, right? 5 over 400. So what is 5 over 400? 1. 5 goes into 120 times, so 1/80th, right? 1/8 is 0.125, so 1/80th is 0.0125, approximately, right? Approximately. These are all approximations. Okay. So what's that? That's about 1/100th of a foot, right? 1/100th of a foot. Well, 1/10th of a foot is about 1.2 inches, right? So 1/100th of a foot is about 1/10th of an inch. Okay? Does that sit well with your intuition? It does for me. If I have a weather balloon that's 10 feet in radius, that's a pretty big weather balloon. That's 20 feet in diameter. It's huge, right? 15 cubic feet is not a lot, right? 15 cubic feet, it's about 90 gallons or something like that, maybe 100 gallons or something like that. So if we have a weather balloon that's 20 feet in diameter, you put about 100 gallons in there, it's going to change about a 1/10 of an inch. Isn't that cool?